This is an abstract representation of a modern software application. High-level code is full of human architectures, nested layers, and deep dependencies. But the processor does not care about your architecture. It only accepts a flat, ultra-dense sequence of raw instructions. On the left is human-readable code, practically perfect, but bloated with human-centric organization the machine doesn't need. Bridging the gap between this organizational bloat and final execution is the primary challenge of optimization. How does a compiler strip away the cost of high-level architecture without changing the program's intent? The answer lies in the absolute governing law of compiler optimization, the as-if rule. The compiler has total authorization to delete your logic, reorder your instructions, or pre-compute your code. The single condition is that the final observable behavior of the program, the memory writes, the inputs, and the outputs, remains completely identical. We are going to step inside the compiler's primary optimization loop to deconstruct how localized mathematical simplifications trigger a cascading global collapse of the codebase. This invisible, destructive process allows developers to prioritize strict organization and extreme readability, trusting the compiler to erase the abstraction cost before the code ever reaches the processor. The first physical stage of AST transformation is normalization. The compiler cleans up the tree and standardizes its shape. Watch this AST node labeled for loop. The compiler performs desugaring, mapping syntactic sugar to foundational logic. It transforms the for loop into a primitive while loop. By collapsing multiple syntaxes into identical while loop node clusters, later optimization stages solve only one specific shape. When the syntactic sugar is highly complex, the compiler must generate entirely new, hidden structures to map the logic. Take this async block. The compiler rewrites this node, expanding it outward into a wide state machine representation that tracks discrete suspension and resumption points across the program. Up to this point, the code isn't actually running faster. The compiler is simply building a smaller, strictly uniform core language that it can easily manipulate. Desugaring acts as a funnel. It forces the unpredictable variety of human expression into a rigid, manageable mathematical baseline. Once the code is standardized, the compiler attempts aggressive mathematical simplification, but it immediately hits a strict barrier, proving purity. In compiler theory, purity is defined as the absolute absence of observable side effects. A pure expression does not write to memory, access I/O, or throw exceptions. The equation 0 multiplied by an unknown function attempts to compress into a single zero node. The compiler rejects this. The node bursts open, revealing a hidden memory write. Deleting the call skips that write, directly violating the as-if rule. This forces the compiler into a default defensive posture. It must assume the absolute worst-case scenario for any unknown variable or external function. Multi-threading and language memory models place massive constraints on what a compiler is legally allowed to alter. Simply deleting a redundant read of a shared variable could inadvertently introduce a race condition if another thread expects to observe that read in a parallel execution environment. Floating point math introduces a major trap. This geometric visualization shows why calculating a plus b, then adding c, results in a physically different value than adding a to the sum of b and c. Floating point operations lose precision and are strictly non-associative. Compilers offer specific override flags for developers who willingly accept the risk of mathematically inaccurate results in exchange for pure computation speed. The compiler's primary directive is never speed, it is safety. A compiler will permanently reject an optimization and choose to output a slow program rather than a fast, broken one. When the compiler successfully proves a section of code is pure, it unleashes a sequence of direct mathematical reductions. The first is constant folding. The compiler pre-computes static equations at compile time. Leaf nodes 3 and 5 merge upward, replacing their parent with an 8 node. This triggers constant propagation. The 8 duplicates and travels down the graph, permanently replacing the variable x. Modern programming languages default to immutability to feed this specific mechanism. Guaranteeing a value never changes allows the compiler to propagate it infinitely. As constant values spread through the tree, they reveal sections of the program that can never be reached, triggering dead code elimination. Dead code includes unreachable conditional branches, unread variables, or abandoned functions. Here, an if-false condition is evaluated, and the entire subtree below it instantly deletes itself from the graph. The cleanup accelerates. Nested ifs flatten into single checks. Complex logic is chopped in half. Unread variables are completely erased. The limitation here is that these three mechanisms are strictly localized. They instantly shut down the moment the code attempts to call an external function. On their own, folding, propagation, and elimination are trivial high school math rules. But chained together, they form a continuous engine that ruthlessly shreds bloated logic. Function calls act as impenetrable black boxes that halt the spread of constants dead in their tracks. Watch this constant value traveling down the AST. It hits an opaque function call node, bounces off, and the propagation flow stops. A standard function call carries a heavy systemic cost. The machine must save registers, build stack frames, and assume shared state is corrupted. To break this barrier, the compiler uses a brute force solution, inlining. The target function's AST graph is dragged in and pasted directly into the current tree. Stalled constants immediately flood the newly pasted nodes, triggering a massive, rapid wave of folding and elimination. Object-oriented code presents a specific challenge here. Indirect method calls routed through virtual tables obscure which function will actually run, blocking the compiler from inlining it. The compiler answers with devirtualization. It attempts to logically prove which subclass implementation will execute ahead of time, turning those indirect calls into direct ones. But aggressive inlining carries a severe trade-off. While it eliminates call overhead, pasting function bodies everywhere exponentially explodes the final binary size, forcing compilers to use strict heuristics to decide what gets merged. Inlining and devirtualization are architectural equalizers. They mathematically erase the performance penalty of splitting software into modular, easily readable components. None of these transformations happen linearly on a checklist. This diagram shows how they exist as a highly reactive cyclical machine. The AST moves continuously around a track consisting of 4 distinct stages: inline, fold, propagate, and eliminate. This continuous cycle is known as fixed-point iteration. It forms a cascading feedback loop. Inlining exposes constants, propagation pushes them forward, folding evaluates math, and elimination drops dead paths. The loop stops when the AST makes a full rotation without changing its shape. There is a darker, dangerous consequence to this extreme optimization logic: undefined behavior. If a program violates language specifications, like overflowing assigned integer, the compiler doesn't throw an error. It mathematically assumes that state never occurs. The as-if rule authorizes the compiler to ruthlessly delete any code following undefined behavior. This creates notorious security bugs, and those specific disasters where code works perfectly in debug mode, but breaks entirely in production. Despite those risks, the ultimate achievement of the entire AST optimization stage is clear. It successfully compresses vast, human-friendly architecture into a lean, mathematically pure reality. But despite the sheer scale of code destroyed here, AST modification is merely the prep work. The code is now ready to be translated into intermediate representation, where true, hardware-aware performance optimization finally begins.